What if I told you that everything you learned in school about how the universe began was incomplete? What if the Big Bang, that moment of cosmic creation we've all been taught as scientific fact, is actually hiding secrets that could fundamentally change how we understand reality itself? Welcome back to the channel. I hope you're having an incredible day, wherever you are in the world. Tonight we're diving into one of the most controversial topics in modern cosmology, one that challenges everything mainstream science has taught us about the origin of everything. And trust me, by the end of this exploration, you're going to see the universe in a completely different light. Before we begin this journey together, I want you to know that the visuals are here to guide you, but feel free to close your eyes, take a deep breath, and let your imagination drift through the cosmos alongside me. There's absolutely no problem if you find yourself drifting off during this exploration. Sometimes the most profound truths reveal themselves when our minds are at their most relaxed and open. I'd also love to know where you're joining me from tonight. Drop your location in the comments below. Are you watching the stars emerge from a bustling city? Or perhaps you're in a quiet countryside where the Milky Way stretches across an unpolluted sky. There's something beautifully fitting about questioning the origins of the universe while we're all scattered across this pale blue dot, each of us under the same ancient cosmic canopy. Now, let me ask you something that might feel unsettling, scientific establishment. The very institutions we trust to unravel the mysteries of existence have been presenting us with an incomplete picture, not out of malice, but because they're trapped within the boundaries of their own paradigms, unable to see beyond the edges of their accepted theories. The Big Bang Theory tells us that roughly 13.8 billion years ago, everything that exists, every atom, every star, every galaxy, emerged from an infinitely dense point, smaller than the period at the end of this sentence. In a fraction of a second, space itself exploded into existence, expanding faster than light, cooling and condensing into the cosmic web we observe today. This narrative has become so deeply embedded in our collective understanding that questioning it almost feels like heresy. We've built entire cosmological models around it, written textbooks about it, and taught generations of students that this is how reality began. The cosmic microwave background radiation serves as its smoking gun, the afterglow of creation itself still echoing through space after nearly 14 billion years. But here's what they don't tell you in those textbooks. What gets glossed over in those polished documentaries? What remains hidden behind the confident proclamations of mainstream cosmology? The Big Bang Theory is riddled with fundamental problems that require increasingly exotic explanations to maintain its validity. Consider this carefully. The theory demands that we accept the existence of dark matter, a mysterious substance that supposedly makes up 85% of all matter in the universe, yet has never been directly detected despite decades of searching. We've built massive underground laboratories, launched sensitive space telescopes, and conducted countless experiments, all in pursuit of these phantom particles that may not exist at all. Then there's dark energy, an even more mysterious force that allegedly drives the accelerating expansion of the universe. This invisible energy supposedly comprises nearly 70% of everything that exists, yet we have no idea what it actually is. Think about that for a moment. Modern cosmology requires us to believe that 95% of the universe consists of things we cannot see, touch, or directly measure. But the problems run deeper than missing matter and energy. The Big Bang Theory faces what cosmologists call the horizon problem. Different regions of the cosmic microwave background, regions that should never have been in causal contact according to the standard model, show identical temperatures to within thousandths of a degree. How can distant parts of the universe that have never communicated with each other be in such perfect thermal equilibrium? The standard answer is cosmic inflation, a theoretical period of exponential expansion that supposedly occurred in the first fraction of a second after the Big Bang. During this brief moment, space itself expanded faster than light, stretching quantum fluctuations to cosmic scales and solving the horizon problem through mathematical sleight of hand. Yet inflation itself raises more questions than it answers. What mechanism drove this exponential expansion? Why did it start? Why did it stop? The theory requires fine-tuning so precise that some physicists have compared it to balancing a pencil on its point for billions of years. Then there's the flatness problem. The universe appears to be geometrically flat to an extraordinary degree of precision. The density of matter and energy falls within an incredibly narrow range that allows space to be neither curved inward like a sphere, nor curved outward like a saddle. The odds of this occurring naturally are so astronomically small that it suggests either incredible fine-tuning or fundamental flaws in our understanding. But perhaps the most troubling aspect of the Big Bang theory is its complete inability to explain what came before. The equations break down at the moment of the supposed singularity, dissolving into mathematical infinities that reveal the theory's limitations. When pressed about what existed before the Big Bang, cosmologists often retreat into philosophical arguments about time itself beginning at that moment, effectively declaring the question meaningless. This is where the shadows, theories begin to emerge from theories that have been marginalized by mainstream academia, despite offering elegant solutions to the problems plaguing the standard model. These alternatives don't require invisible matter or mysterious energy. They don't need fine-tuned inflation or mathematical singularities. Instead, they propose radically different mechanisms for cosmic evolution that challenge our most basic assumptions about space, time, and gravity itself. One of the most compelling alternatives suggests that the universe never had a beginning at all. Instead of a singular moment of creation, these theories propose an eternal cosmos that undergoes cycles of expansion and contraction, or exists in a steady state that maintains its properties over infinite time. In these models, what we interpret as the Big Bang was simply a transition phase in an ongoing cosmic process. Other theories challenge our understanding of gravity itself. What if Einstein's general relativity, for all its elegance and success, is incomplete at cosmic scales? Modified theories of gravity can explain the rotation curves of galaxies without requiring dark matter. They can account for the accelerating expansion without invoking dark energy. They suggest that the universe's behavior on the largest scales follows different rules than we've assumed. An electric universe theory proposes that electromagnetic forces, not gravity, dominate cosmic evolution. In this framework, galaxies are connected by vast plasma currents that shape their structure and behavior. The cosmic microwave background isn't the afterglow of a primordial explosion, but the signature of ongoing electrical processes throughout space. Plasma cosmology suggests that the universe is filled with ionized gas that behaves according to well-understood electromagnetic principles. Laboratory experiments can reproduce cosmic phenomena on smaller scales, providing tangible evidence for electromagnetic processes in space that conventional cosmology struggles to explain. The marginalization of these alternatives reveals something troubling about modern science. Instead of embracing new ideas and challenging existing theories, the scientific community has become increasingly dogmatic, defending the Big Bang theory with almost religious fervor. Careers are built on supporting the standard model, funding flows to research that confirms established theories, and dissenting voices are silenced or ignored. This isn't how science is supposed to work. True scientific inquiry demands skepticism, openness to new ideas, and willingness to abandon cherished theories when evidence suggests they're incomplete or wrong. Yet modern cosmology has become trapped in a paradigm that requires ever more exotic explanations to maintain its viability. Consider how the discovery of cosmic acceleration led not to questioning the Big Bang model, but to inventing dark energy. When galaxy rotation curves didn't match predictions, astronomers didn't reconsider gravitational theory, but instead postulated dark matter. Each new observation that challenges the standard model results in adding another invisible component, rather than questioning fundamental assumptions. This pattern reveals the theory's weakness, not its strength. A robust scientific theory should make clear, testable predictions that can be verified or falsified through observation. Instead, the Big Bang theory has become increasingly unfalsifiable, capable of accommodating any observation through the addition of new parameters or invisible components. The time has come to seriously consider whether we've been led astray by a beautiful but fundamentally flawed theory. The Big Bang narrative appeals to our desire for cosmic origins, our need to understand how everything began. It provides a comforting story of creation that resonates with our deepest myths and religious traditions. But comfort isn't truth, and beauty isn't evidence. The universe doesn't owe us a simple, comprehensible origin story. Reality might be far stranger and more complex than the Big Bang theory suggests, operating according to principles we've yet to discover or understand. As we continue this exploration in the next part, we'll delve deeper into the specific evidence that challenges the Big Bang model and examine the alternative theories that could revolutionize our understanding of cosmic evolution. We'll look at the observations that don't fit the standard model, the mathematical problems, its foundations that plague, and the compelling explanations offered by theories that mainstream science has chosen to ignore. The universe is vast and mysterious, filled with phenomena that stretch our understanding to its limits. Perhaps it's time to acknowledge that our current theories, for all their mathematical elegance, might be missing something fundamental about the nature of reality itself. What if the very tools we use to peer into the cosmic past are revealing a story that contradicts the narrative we've been told? The deeper we look into space, the further back in time we see, and what astronomers are discovering doesn't match the predictions of Big Bang cosmology. Instead of a universe that started simple and grew complex over time, we're finding fully formed galaxies and massive structures that shouldn't exist according to the standard timeline. The James Webb Space Telescope has shattered expectations by revealing galaxies that appear surprisingly mature and organized for objects we're seeing as they existed just a few 100 million years after the supposed Big Bang. These aren't the primitive, chaotic structures that should characterize the early universe. Instead, they display the kind of sophisticated architecture that should have taken billions of years to develop. Traditional cosmology tells us that the first stars were massive, short-lived giants that burned bright and died young, seeding space with heavier elements through spectacular supernovae. Only after several generations of stellar death and rebirth could the universe produce the complex chemistry necessary for planets and life. Yet we're observing galaxies in the early universe that already contain these heavy elements in abundances that challenge this sequential narrative. The cosmic web itself presents another puzzle that the Big Bang theory struggles to address. This vast network of filaments and voids, stretching across billions of light years, displays a level of organization that seems impossible to achieve through the random processes described by standard cosmology. Computer bang parameter simulations based on big can't reproduce the large-scale structure we actually observe. Consider the Great Wall of Galaxies, a massive structure spanning over 500 million light-years. According to Big Bang cosmology, there simply hasn't been enough time since the universe began for gravity to pull matter together on such enormous scales. The formation of this structure would require more time than the universe is supposed to have existed. Similarly, the Sloan Great Wall and other cosmic megastructures challenge our understanding of how quickly matter can organize itself. These aren't small deviations from predictions, but fundamental contradictions that suggest something is seriously wrong with our cosmic timeline. The Redshift observations that originally supported the Big Bang interpretation deserve closer scrutiny as well. When Edwin Hubble first observed that distant galaxies showed redshifted light, the natural interpretation was that they were moving away from us due to the expansion of space itself. This became the foundation for the expanding universe model and ultimately the Big Bang theory. But redshift doesn't necessarily indicate recession velocity. Light can be redshifted through other mechanisms that have nothing to do with cosmic expansion. Tired light theories suggest that photons lose energy during their journey across vast distances through interactions with particles or fields in space. Gravitational redshift occurs when light climbs out of deep gravitational wells, stretching its wavelength in the process. Intrinsic redshift mechanisms propose that the redshift we observe might be related to the age or properties of the objects themselves rather than their distance or velocity. Some galaxies show quantized redshift values that cluster around specific numbers, a pattern that would be extremely unlikely if redshift were purely due to random recession velocities in an expanding universe. The cosmic microwave background radiation, often cited as the strongest evidence for the Big Bang, deserves careful re-examination as well. While this uniform radiation does permeate space, its origin might not be the afterglow of a primordial fireball. Alternative explanations suggest it could be the result of ongoing processes in the cosmos, such as the thermalization of starlight over vast periods of time, or the interaction of matter and radiation in steady-state conditions. The slight temperature variations in the cosmic microwave background, which supposedly represent the seeds of all cosmic structure, might actually reflect present-day phenomena rather than ancient fluctuations. The patterns we observe could be influenced by our local environment, the structure of our galaxy, or other foreground effects that contaminate what we assume to be a pristine view of the early universe. These observational challenges to the Big Bang model aren't isolated anomalies that can be explained away with minor adjustments to the theory. They represent fundamental contradictions that suggest we're viewing the universe through a distorted lens, one that forces us to invoke increasingly exotic and undetectable components to maintain the illusion of theoretical consistency. The scientific method demands that we follow the evidence wherever it leads, even when it challenges our most cherished beliefs about reality. Yet the astronomical community has shown remarkable resistance to questioning the Big Bang paradigm, preferring to add new layers of complexity rather than considering simpler alternatives that don't require invisible matter and energy. This resistance isn't purely scientific. There are social, professional, and economic factors at play. Entire careers have been built on Big Bang cosmology. Massive research programs, expensive observatories, and prestigious institutions depend on funding that flows toward projects that support the standard model. Challenging the fundamental assumptions of modern cosmology isn't just intellectually difficult, it's professionally dangerous. Graduate students learn that questioning the Big Bang is career suicide. Researchers who propose alternative theories find their papers rejected by mainstream journals, their grant applications denied, and their ideas marginalized by the scientific establishment. This creates an echo chamber where dissenting voices are silenced and contrary evidence is dismissed or ignored. The peer review process, which should serve as a quality control mechanism for scientific research, has become a barrier to revolutionary ideas. Papers that challenge the standard model are often rejected not on their scientific merits, but because they contradict established dogma. Reviewers, themselves invested in the current paradigm, are naturally biased against theories that would invalidate their own work. This institutional resistance to change isn't unique to cosmology. Throughout history, scientific revolutions have faced similar opposition from established authorities who had invested their reputations in the prevailing theories. The transition from geocentric to heliocentric models, from Newtonian to relativistic physics, and from static to dynamic genetics, all encountered fierce resistance before eventually being accepted. But unlike previous scientific revolutions, which could be validated through direct experimentation or observation, cosmology deals with phenomena that are largely beyond our ability to test directly. We can't create universes in laboratories or travel to distant galaxies to verify our theories. This makes cosmology particularly vulnerable to theoretical dogma and resistant to paradigm shifts. The mathematical complexity of modern cosmological theories also creates barriers to understanding and criticism. The equations governing general relativity, quantum field theory, and cosmic inflation are so complex that only specialists can truly comprehend them. This technical barrier allows experts to dismiss criticism from outside their field while protecting their theories from scrutiny by the broader scientific community. Yet some of the most important insights in science have come from outsiders who weren't constrained by conventional thinking. The amateur astronomers who first observed stellar parallax, the patent clerk who revolutionized physics, and the geologist who proposed continental drift all faced initial rejection from established experts who couldn't see beyond their own assumptions. The current crisis in cosmology demands this kind of fresh perspective. We need researchers who are willing to question fundamental assumptions, explore alternative mechanisms, and follow the evidence even when it leads to uncomfortable conclusions. We need institutions that support genuinely independent research, rather than projects designed to confirm existing theories. The stakes couldn't be higher. Our understanding of the universe's origin and evolution shapes how we see ourselves, our place in the cosmos, and our ultimate destiny as a species. If we're wrong about these fundamental questions, we're not just making academic errors. We're building our entire worldview on false foundations. The evidence suggests that the universe might be far older, more complex, and more mysterious than the Big Bang theory allows. Instead of a finite cosmos with a definite beginning, we might inhabit an eternal universe that has existed forever, undergoing continuous evolution without the need for a singular moment of creation. This possibility opens up profound questions about the nature of existence itself. If the universe has no beginning, what does that mean for causality, for the arrow of time, for our understanding of physical law? These aren't just scientific questions, they're philosophical ones that touch the very core of human experience and meaning. As we prepare to explore these alternative visions of cosmic reality, we must be willing to let go of comfortable certainties and embrace the possibility that everything we thought we knew about the universe might be incomplete or wrong. The truth, whatever it might be, is worth pursuing regardless of how much it challenges our current beliefs. The cosmos doesn't care about our theories or our need for simple explanations. It exists according to its own rules, following principles that might be far stranger and more wonderful than anything we've yet imagined. Our job as seekers of truth is to observe carefully, think clearly, and remain open to possibilities that extend far beyond the boundaries of current scientific orthodoxy. The journey toward truth requires courage, especially when that truth threatens to upend everything we've been taught to believe. As we venture deeper into this cosmic mystery, we must confront the uncomfortable possibility that the scientific establishment has been operating under a collective delusion, one so pervasive and deeply rooted that questioning it feels like challenging reality itself. But what if reality is far stranger and more magnificent than the Big Bang narrative allows? What if the universe operates according to principles that our current theories can't even begin to comprehend? The deeper we dig into the evidence, the more we discover patterns that suggest a fundamentally different cosmic story, one that's been hiding in plain sight while we've been mesmerized by mathematical equations and theoretical abstractions. Let's examine something that should give us serious pause: the age problem that mainstream cosmology desperately tries to ignore. We're discovering objects in space that appear to be older than the universe itself, according to Big Bang calculations. Globular clusters, those ancient stellar communities that orbit our galaxy, show evidence of being 15 to 16 billion years old. How can objects exist that predate the supposed moment of creation by billions of years? The standard response involves adjusting parameters, fine-tuning models, and invoking measurement uncertainties. But these aren't minor discrepancies that can be explained away with better instruments or refined calculations. These are fundamental contradictions that strike at the heart of our cosmic timeline. Consider the white dwarf cooling problem. White dwarf stars are stellar remnants that cool predictably over time, acting like cosmic clocks that should tell us how long they've been cooling since their formation. The oldest white dwarfs we observe indicate cooling periods that extend far beyond what the Big Bang timeline permits. These ancient stellar corpses are whispering secrets about a universe that's been evolving for far longer than we're supposed to believe. Then there's the mystery of population 3 stars, those theoretical first-generation giants that supposedly formed from pure hydrogen and helium in the early universe. Despite decades of searching with increasingly powerful telescopes, we've never found a single example of these primordial stars. They remain purely theoretical constructs, necessary for the Big Bang model, but absent from observed reality. This absence isn't just puzzling, it's devastating to the standard narrative. Without population 3 stars, there's no mechanism for creating the heavier elements we observe in supposedly ancient galaxies. The chemical evolution timeline collapses, leaving us with mature cosmic structures that shouldn't exist, according to the theory that's supposed to explain them. The surface brightness problem presents another challenge that cosmologists prefer not to discuss in public. As we look deeper into space and further back in time, galaxies should appear progressively smaller and dimmer according to standard cosmological models. Yet distant galaxies maintain surface brightness levels that violate these predictions, suggesting that either our understanding of cosmic distances is wrong, or the expansion model itself is flawed. Galaxy formation simulations reveal the desperate lengths to which theorists will go to preserve their cherished model. These computer programs require constant adjustment of parameters, injection of artificial feedback mechanisms, and fine-tuning of initial conditions to produce anything resembling the cosmic structures we actually observe. The fact that such extensive manipulation is necessary suggests that the underlying theory might be fundamentally incorrect. The missing satellite problem illustrates this theoretical crisis perfectly. Dark matter simulations predict that galaxies like our Milky Way should be surrounded by thousands of small satellite galaxies, yet we observe only a few dozen. Rather than questioning whether dark matter exists, theorists invoke increasingly complex mechanisms to explain why these predicted satellites remain invisible. Quantized redshift observations pose another serious challenge to the expanding universe interpretation. Astronomer Halton Arp spent decades documenting cases where galaxies with dramatically different redshifts appear physically connected by bridges of matter or show clear gravitational interactions. According to Big Bang cosmology, these objects should be separated by billions of light years, making such connections impossible. Arp's observations suggest that redshift might not indicate distance or recession velocity at all. Instead, it could be an intrinsic property of matter that changes over time or varies according to physical processes we don't yet understand. This possibility would invalidate the entire foundation of modern cosmological distance measurements and cosmic age calculations. The scientific establishment's response to Arp's work reveals the institutional bias that pervades modern astronomy. Rather than investigating his findings or attempting to replicate his observations, the community marginalized him, denied him telescope time, and effectively ended his career. His data remains largely ignored, dismissed as anomalous without serious consideration of what it might reveal about the true nature of cosmic redshift. This pattern of suppression extends to other researchers who've presented evidence contradicting the standard model. Plasma cosmologists who demonstrate that electromagnetic forces can explain galactic structure without requiring dark matter find their papers rejected by mainstream journals. Steady-state theorists who propose elegant alternatives to Big Bang cosmology are relegated to fringe conferences and obscure publications. The electric universe model offers particularly compelling explanations for phenomena that puzzle conventional astronomers. Laboratory plasma physics experiments can reproduce spiral galaxy structures, explain stellar formation mechanisms, and demonstrate how electromagnetic forces shape cosmic architecture. These aren't theoretical abstractions, but observable, reproducible phenomena that scale naturally from laboratory to cosmic dimensions. Plasma cosmology recognizes that 99% of the visible universe consists of ionized gas that responds to electromagnetic fields according to well-understood principles. Unlike the mysterious dark matter and dark energy that supposedly dominate the cosmos, plasma behaves according to laws we can study directly in laboratory settings. The filamentary structure of the cosmic web mirrors the behavior of plasma discharge patterns observed in high-voltage laboratory experiments. The spiral arms of galaxies follow magnetic field lines that channel plasma currents across vast distances. The formation of stars and planets occurs through electromagnetic pinch effects that concentrate matter far more efficiently than gravity alone could achieve. These electromagnetic processes operate on timescales that dwarf the supposed age of the Big Bang universe. Plasma structures can persist for hundreds of billions of years, evolving slowly according to electromagnetic principles, rather than requiring rapid formation through gravitational collapse. This extended timeline easily accommodates the mature structures we observe in supposedly young regions of the cosmos. Steady-state cosmology offers another compelling alternative that eliminates many of the problems plaguing Big Bang theory. Instead of requiring a singular moment of creation, steady-state models propose that the universe maintains constant average density through continuous matter creation. As space expands, new matter appears to fill the growing volume, maintaining cosmic properties over infinite time. This continuous creation occurs at such a slow rate that it would be undetectable by current instruments, requiring only one hydrogen atom per cubic meter of space every few billion years. While this might seem exotic, it's far less problematic than invoking dark matter particles that have never been detected, or dark energy fields that violate known physics. Steady-state models naturally explain the cosmic microwave background as thermalized starlight rather than primordial radiation. Over infinite time, stellar radiation would reach thermal equilibrium throughout space, producing the uniform background we observe without requiring a hot, dense beginning. The quasi-steady state cosmology developed by Fred Hoyle and his colleagues addresses some of the observational challenges that led to the original steady-state theory's decline. This refined version incorporates oscillating creation rates that can account for the apparent evolution of cosmic structures while maintaining the elegance of an eternal universe. Cyclic cosmology presents yet another alternative that eliminates the need for a singular beginning. These models propose that the universe undergoes repeated cycles of expansion and contraction, with each cycle lasting hundreds of billions of years. What we interpret as the Big Bang was merely the most recent bounce in an eternal sequence of cosmic oscillations. Ekpyrotic scenarios, derived from string theory, suggest that our universe resulted from the collision of higher dimensional spaces called branes. These collisions occur periodically, creating new cosmic cycles without requiring the universe to collapse to a singular point. The energy released during these collisions could explain the cosmic microwave background and the formation of large-scale structure. Pre-Big Bang cosmology, developed by physicists like Gabriele Veneziano, proposes that our current expansion phase was preceded by a contracting phase that lasted for an indefinite period. The transition between contraction and expansion occurred through string-theoretic mechanisms that avoid the mathematical singularities that plague standard Big Bang models. These alternative theories aren't just mathematical curiosities or desperate attempts to avoid uncomfortable conclusions. They're serious scientific proposals that address real observational challenges while offering elegant explanations for cosmic phenomena. The fact that they've been marginalized by mainstream astronomy reveals more about institutional bias than about their scientific merit. The suppression of alternative cosmological theories represents a failure of the scientific method itself. Science is supposed to progress through the open exchange of ideas, rigorous testing of hypotheses, and honest evaluation of evidence. Instead, we've created an orthodoxy that protects established theories from legitimate criticism while silencing dissenting voices. This institutional capture of cosmology has profound implications for human understanding. We're not just getting the details wrong about cosmic evolution, we're potentially missing fundamental truths about the nature of reality itself. The universe might be telling us a completely different story than the one we've chosen to hear. The evidence suggests that we inhabit a cosmos far more ancient, mysterious, and magnificent than the Big Bang narrative allows. Instead of a universe born from a singular explosion 13.8 billion years ago, we might be part of an eternal cosmic dance that has been unfolding for timescales that dwarf human comprehension. This possibility should fill us with wonder rather than fear. An eternal universe means that cosmic evolution operates according to principles we've barely begun to explore. The structures we observe, from galaxies to galaxy clusters to the cosmic web itself, represent the products of processes that have had infinite time to develop their intricate complexity. The implications extend far beyond astronomy and cosmology. If the universe has no beginning, then causality itself might operate according to different principles than we've assumed. The arrow of time, the nature of physical law, and the relationship between mind and matter all become open questions that demand fresh investigation. The truth about cosmic origins might be hiding in plain sight, waiting for minds brave enough to question established dogma, and eyes clear enough to see beyond the mathematical abstractions that have obscured our vision. The universe is calling us to look deeper, think more clearly, and embrace possibilities that extend far beyond the comfortable boundaries of current scientific consensus. What we're witnessing is nothing short of a cosmic conspiracy of silence, where the most profound questions about our existence are being answered with mathematical smoke and mirrors, rather than honest scientific inquiry. The deeper we venture into this rabbit hole, the more we discover that the Big Bang theory isn't just incomplete, it's actively preventing us from understanding the true nature of our cosmic home. Let me share with you something that should make every thinking person pause and reconsider everything they've been told about the universe's origins. The lithium problem represents one of the most glaring contradictions in Big Bang nucleosynthesis, yet it's rarely discussed in popular science presentations. According to the theory's predictions, the early universe should have produced specific amounts of light elements during those first crucial minutes after creation. The calculations are precise and seemingly elegant. Big Bang nucleosynthesis should have created roughly 75% hydrogen, 25% helium, and trace amounts of lithium and other light elements. The hydrogen and helium observations match reasonably well, which is why cosmologists celebrate these as confirmations of their model. But lithium presents a devastating problem that threatens the entire framework. We observe only about 1 Bang theory predicts should exist in the third of the lithium that big oldest stars. This isn't a minor discrepancy that can be explained away with measurement uncertainties or stellar evolution effects. It's a factor of 3 difference that strikes at the heart of our understanding of primordial nucleosynthesis. Various attempts have been made to explain this lithium deficit. Some theorists propose that unknown stellar processes destroy lithium after formation, while others suggest that exotic physics during the early universe modified the predicted abundances. These explanations require increasingly complex mechanisms that strain credibility and violate the principle of scientific simplicity. The lithium problem becomes even more troubling when we consider that it's not an isolated anomaly, but part of a pattern of observational failures that plague Big Bang cosmology. Each time observations contradict theoretical predictions, the response isn't to question the fundamental model, but to add new parameters, invoke unknown physics, or dismiss the observations as somehow flawed. This approach violates the basic principles of scientific methodology that should guide our quest for truth. A robust theory should make testable predictions that can be verified clear through observation. When predictions fail repeatedly, the theory itself should be questioned, not rescued through increasingly elaborate modifications. Consider the cosmic microwave background temperature fluctuations that supposedly represent the seeds of all cosmic structure. These tiny variations, measured to extraordinary precision by space-based observatories, are held up as smoking gun evidence for the Big Bang model of these fluctuations requires assumptions about, but the interpretation cosmic geometry, expansion history, and the nature of matter that aren't independently verified. Alternative explanations for the cosmic microwave background patterns don't require a primordial fireball or exotic inflation mechanisms. The uniform temperature could result from thermalization processes occurring over vast timescales in an eternal universe. The small-scale fluctuations might reflect ongoing astrophysical processes rather than ancient quantum fluctuations stretched to cosmic scales. The polarization patterns in the cosmic microwave background, which supposedly provide additional confirmation of inflation theory, could equally well be explained by electromagnetic processes in the cosmic plasma that pervade space. The magnetic fields threading the galaxy and beyond would naturally create polarization signatures that mimic those attributed to gravitational waves from the inflationary epoch. These alternative interpretations aren't given fair consideration because they challenge the theoretical framework that dominates modern cosmology. The scientific establishment has invested so heavily in the Big Bang paradigm that questioning its fundamental assumptions has become tantamount to professional heresy. The peer review process, which should serve as a quality control mechanism for scientific research, has become a barrier to revolutionary ideas. Reviewers who've built their careers on Big Bang cosmology are naturally reluctant to approve papers that would invalidate their life's work. This creates a self-reinforcing cycle where only research supporting the established paradigm receives funding and publication. Graduate students quickly learn that questioning fundamental assumptions about cosmic origins is career suicide. They're trained to work within the accepted framework, solving technical problems and refining existing models rather than exploring genuinely alternative approaches. This educational system produces specialists who can manipulate complex equations but lack the conceptual flexibility to envision radically different cosmological scenarios. The mathematical complexity of modern cosmological theories also serves as a barrier to criticism. The equations governing general relativity, quantum field theory, and cosmic inflation are so intricate that only a small community of experts can fully understand them. This technical barrier allows specialists to dismiss criticism from outside their field while protecting their theories from broader scrutiny. Yet some of the most important breakthroughs in science have come from researchers who weren't constrained by conventional thinking. The amateur astronomers who first measured stellar parallax, the patent clerk who revolutionized our understanding of space and time, and the meteorologist who proposed continental drift all faced initial rejection from established experts who couldn't see beyond their own assumptions. The current crisis in cosmology demands this kind of fresh perspective. We need researchers willing to question fundamental assumptions, explore alternative mechanisms, and follow evidence even when it leads to uncomfortable conclusions. We need institutions that support genuinely independent research rather than projects designed to confirm existing theories. The observational evidence supporting alternative cosmological models continues to accumulate despite institutional resistance. Intrinsic redshift phenomena, documented by numerous researchers, suggest that cosmic distances might be fundamentally different from what standard cosmology assumes. If redshift doesn't always indicate recession velocity, then our entire cosmic distance scale becomes questionable. The tired light hypothesis offers a compelling explanation for cosmic redshift that doesn't require space expansion or a Big Bang origin. As photons travel across vast distances, they could lose energy through interactions with particles, fields, or the quantum vacuum itself. This energy loss would manifest as redshift that increases with distance, exactly what we observe without requiring the universe to expand. Laboratory experiments have demonstrated mechanisms by which photons can lose energy during propagation through various media. While the interstellar medium might seem too sparse to produce significant effects, the cumulative impact over billions of light years could easily account for the redshifts we attribute to cosmic expansion. Plasma redshift mechanisms offer another intriguing possibility. As light passes through regions of ionized gas pervaded by magnetic fields, it could undergo frequency shifts that depend on the plasma properties and field configurations. Given that most of the visible universe consists of plasma, such effects could significantly modify the light we receive from distant objects. The Wolf effect, discovered in atomic physics, shows how light scattering in moving media can produce redshifts that don't correspond to source velocities. Similar phenomena might occur on cosmic scales as starlight passes through turbulent regions of the interstellar and intergalactic medium, creating apparent recession velocities that don't reflect actual motion. These alternative redshift mechanisms don't require the exotic physics of cosmic inflation, dark matter, or dark energy. They operate according to well-understood principles that can be studied in laboratory settings and scaled to cosmic dimensions. The fact that they're not seriously considered by mainstream cosmology reveals the theoretical bias that pervades the field. Variable mass theories present another class of alternatives that eliminate many problems of standard cosmology. If fundamental particles had different masses in the past, or if the constants of physics evolved over cosmic time, then our interpretation of distant observations would need radical revision. If the fine structure constant, which governs electromagnetic interactions, varied slightly over cosmic time, then the light we receive from distant objects would show subtle spectral shifts that could be misinterpreted as Doppler redshift. Such variations might explain apparent cosmic acceleration without requiring dark energy. Similarly, if with cosmic epoch gravitational coupling varied, then the dynamics of distant galaxies and clusters would differ from local behavior in ways that could mimic the effects attributed to dark matter. Variable gravity theories can naturally explain galactic rotation curves and cluster dynamics without invoking invisible particles. These theoretical possibilities aren't mere speculation, but are being actively investigated by researchers brave enough to challenge conventional wisdom. The fact that such alternatives aren't widely known or discussed reveals the narrow scope of ideas permitted within mainstream cosmological discourse. The suppression of alternative theories has created a false consensus that mistakes theoretical conformity for scientific rigor. True scientific progress requires diversity of thought, open debate, and willingness to abandon cherished ideas when evidence demands revision. The current state of cosmology violates these principles, creating an intellectual monoculture that stifles innovation and discovery. Breaking free from this theoretical straitjacket requires more than just technical expertise. It demands intellectual courage and philosophical flexibility. We must be willing to question our most basic assumptions about space, time, matter, and causality. We must embrace the possibility that reality operates according to principles far stranger and more wonderful than our current theories suggest. The universe doesn't owe us simple explanations or comfortable narratives about cosmic origins. It exists according to its own rules, following principles that might be fundamentally alien to human intuition and mathematical convenience. Our job as seekers of truth is to observe carefully, think clearly, and remain open to possibilities that extend far beyond current scientific orthodoxy. As we approach the culmination of this exploration, we must confront the profound implications of what we've discovered. If the Big Bang Theory is indeed a magnificent delusion, then our entire worldview requires fundamental revision. The cosmos might be eternal rather than created, electric rather than gravitational, conscious rather than mechanical. These possibilities shouldn't terrify us, but inspire us with wonder at the magnificent complexity and mystery of existence. An eternal universe offers infinite time for cosmic evolution, allowing structures and processes to develop complexity beyond our current imagination. An electric cosmos suggests that consciousness and intelligence might be fundamental features of reality rather than accidental byproducts of material evolution. The journey toward truth requires courage, especially when that truth threatens to upend everything we've been taught to believe. But the alternative, continuing to build our understanding on false foundations, ultimately leads to intellectual stagnation and spiritual impoverishment. The cosmos is calling us to look deeper, think more clearly, and embrace possibilities that extend far beyond the comfortable boundaries of current scientific consensus. The real universe, whatever its true nature might be, is almost certainly stranger and more magnificent than anything we've yet dared to imagine. As we prepare for our final exploration of these cosmic mysteries, remember that questioning established dogma isn't an act of rebellion, but an expression of the highest scientific values. Truth doesn't fear investigation, and genuine knowledge welcomes challenges that test its foundations. The universe has been patiently waiting for minds brave enough to see beyond theoretical abstractions and mathematical constructions to glimpse the deeper reality that underlies all phenomena. That reality might be far more mysterious and wonderful than the Big Bang narrative suggests, offering insights into the nature of existence that could revolutionize human understanding and transform our relationship with the cosmos itself. The path we've been walking together tonight has led us to a precipice where comfortable certainties dissolve and profound mysteries emerge from the shadows. What we're about to explore will challenge not just your understanding of cosmic origins, but your entire conception of what it means to exist in this vast, enigmatic universe. As you settle deeper into this exploration, perhaps feeling the gentle pull of sleep at the edges of your consciousness, allow yourself to drift with these ideas. Sometimes the most profound revelations come when our analytical minds relax their grip and deeper intuitive understanding begins to surface. The electric universe model represents perhaps the most radical departure from conventional cosmology, yet it offers explanations for cosmic phenomena that are both elegant and testable. Unlike the invisible dark matter and mysterious dark energy that dominate standard models, electromagnetic forces operate according to principles we can observe and verify in laboratory settings. Consider the breathtaking spiral structure of galaxies, those magnificent cosmic pinwheels that have captivated human imagination since we first glimpsed them through telescopes. Standard cosmology struggles to explain how these delicate structures could maintain their form over billions of years. Gravitational models predict that spiral arms should wind up and disappear within a few 100 million years. Yet we observe pristine spirals throughout the cosmos. The electric universe provides a compelling solution. Plasma currents flowing along magnetic field lines naturally create and maintain spiral patterns that can persist indefinitely. Laboratory plasma experiments routinely produce spiral structures that scale beautifully to galactic dimensions, suggesting that the same electromagnetic principles governing small-scale phenomena also shape the largest structures in space. These plasma currents don't just create spiral arms, they channel matter and energy across vast distances, connecting galactic cores to their outer regions through invisible electromagnetic circuits. The energy flowing through these circuits could power the phenomena we observe in active galactic nuclei without requiring supermassive black holes or exotic physics. The jets of material streaming from galactic centers, extending for hundreds of thousands of light years with remarkable collimation and stability, become natural consequences of electromagnetic pinch effects rather than mysterious products of gravitational acceleration. These jets follow magnetic field lines like cosmic transmission cables, carrying energy and matter across intergalactic distances. Star formation itself might operate through electromagnetic rather than purely gravitational mechanisms. The conventional model requires mysterious dark matter to provide the gravitational scaffolding necessary for gas clouds to collapse and form stars. But electromagnetic forces can compress plasma far more efficiently than gravity alone, creating the conditions for stellar ignition without invoking invisible matter. The periodic arrangement of stars within galaxies, unexpected the abundance of heavy elements in supposedly young stellar populations, and the rapid formation of complex structures all become comprehensible when we recognize that electromagnetic forces dominate cosmic evolution. These forces operate on timescales that dwarf the supposed age of the Big Bang universe, allowing for the gradual development of the intricate cosmic architecture we observe. Plasma cosmology extends this electromagnetic perspective to the largest scales, proposing that the cosmic web itself results from the interaction of vast plasma currents flowing through space. The filamentary structure connecting galaxy clusters mirrors the behavior of plasma discharges in laboratory experiments, suggesting that electromagnetic forces, rather than dark matter, create the scaffolding upon which cosmic structure hangs. This electromagnetic cosmos eliminates many of the paradoxes that plague standard cosmology. There's no need to explain how the universe achieved thermal equilibrium across regions that supposedly never communicated with each other. Electromagnetic forces propagate at light speed, allowing different regions of an eternal universe to reach thermal balance over sufficient time. The cosmic microwave background becomes not the afterglow of creation, but the natural consequence of thermalization processes occurring over vast periods in plasma-filled space. The slight temperature variations we observe could reflect ongoing electromagnetic phenomena rather than ancient quantum fluctuations from an inflationary epoch. But perhaps the most profound implication of electric universe theory concerns the nature of consciousness itself. If electromagnetic fields pervade and shape cosmic structure, then the bioelectric phenomena underlying consciousness and life might be fundamental features of reality rather than accidental emergences from purely material processes. The human brain operates as an electromagnetic system, generating complex field patterns that somehow give rise to thoughts, emotions, and self-awareness. If similar electromagnetic processes occur throughout the cosmos, then consciousness might be woven into the very fabric of space and time. This possibility opens breathtaking vistas for understanding our place in the universe. Instead of being isolated accidents in a hostile cosmos, we might be integral parts of a conscious universe that has been evolving and developing awareness for timescales beyond human comprehension. Steady-state cosmology offers another pathway beyond the limitations of Big Bang thinking, proposing that the universe maintains constant average properties through continuous creation of matter and energy. This creation occurs so slowly that it would be undetectable by current instruments, requiring only the appearance of one hydrogen atom per cubic meter of space every few billion years. While this might seem exotic, continuous creation is far less problematic than invoking particle types that have never been detected, or energy fields that violate conservation laws. The steady-state universe eliminates the need for a singular moment of creation, while naturally explaining the apparent youth and vitality we observe in supposedly ancient regions of the cosmos. Fred Hoyle, one of the architects of steady-state theory, recognized that continuous creation could operate through quantum mechanical processes that we're only beginning to understand. The quantum vacuum, far from being empty space, seethes with virtual particles that briefly materialize before vanishing back into the void. Under certain conditions, these quantum fluctuations might become permanent, adding new matter universe. This process to the expanding would be completely natural, requiring no violation of physical laws or appeal to supernatural intervention. It would operate according to principles that emerge from our growing understanding of quantum field theory and the fundamental nature of space-time itself. The quasi-steady-state cosmology developed by Hoyle and his colleagues addresses some of the observational challenges that led to the original theory's decline while preserving its essential insights. This refined version incorporates oscillating creation rates that can account for the apparent evolution we observe in cosmic structures while maintaining the elegance of an eternal universe. In this model, creation doesn't occur uniformly throughout space, but concentrates in specific regions where conditions favor the materialization of new matter. These creation events could explain the formation of quasars, active galactic nuclei, and other energetic phenomena without requiring exotic physics or impossible energy densities. The implications extend far beyond technical cosmology into the deepest questions about existence itself. An eternal universe with ongoing creation suggests that reality is fundamentally creative, constantly bringing forth new possibilities and expressions. We're not witnessing the gradual decay of an initially perfect creation, but participating in an ongoing cosmic symphony that has been composing itself for infinite time. Cyclic cosmology presents yet another alternative that eliminates the need for absolute beginnings while accounting for the apparent evolution we observe. These models propose that the universe undergoes repeated cycles of expansion and contraction, with each cycle lasting hundreds of billions of years. What we interpret as the Big Bang was merely the most recent bounce in an eternal sequence of cosmic oscillations. The universe contracts under the influence of attractive forces until it reaches a minimum size, then rebounds into a new expansion phase. This process could continue indefinitely, with each cycle potentially lasting far longer than the supposed age of the current universe. The rebound mechanism doesn't require the universe to collapse to a mathematical singularity, avoiding the infinities that plague standard Big Bang models. Instead, quantum effects or exotic physics prevent complete collapse, causing the universe to bounce back before reaching zero size. These cycles could explain the apparent fine-tuning of physical constants without requiring multiple universes or anthropic arguments. If the universe has undergone countless cycles, physical parameters might gradually evolve toward values that support complexity and structure formation. The constants we observe could be the natural result of cosmic evolution rather than incredible coincidences. Each cycle might leave subtle traces in the cosmic microwave background or large-scale structure that we're only beginning to detect. Advanced civilizations from previous cycles might have encoded information in gravitational waves or other long-lasting phenomena, creating a cosmic archaeological record spanning multiple universal epochs. The philosophical implications of cyclic cosmology are profound. Instead of facing heat death or big rip scenarios, the universe repeatedly renews itself, ensuring that complexity, life, and consciousness have infinite opportunities to emerge and flourish. Death becomes transformation rather than termination, part of an endless cycle of cosmic renewal. Pre-Big Bang scenarios derived from string theory and other advanced theoretical frameworks propose that our current expansion phase was preceded by a contracting phase that lasted for indefinite periods. These models suggest that time itself might be eternal, extending infinitely into both past and future. The Big Bang becomes not the beginning of time, but a transition between different phases of cosmic evolution. This eliminates the paradox of asking what came before time began while preserving the observational successes of expansion cosmology. Ekpyrotic scenarios propose that our universe resulted from the collision of higher dimensional membranes, or brains, floating in a space of extra dimensions. These collisions occur periodically, creating new cosmic cycles without requiring complete gravitational collapse. The energy released during brain collisions could explain the cosmic microwave background, the formation of large-scale structure, and the apparent flatness of space without invoking inflation or other exotic mechanisms. Each collision creates a new universe with potentially different physical laws and constants, contributing to a multiverse of incredible diversity. These string-theoretic models operate in mathematical frameworks so advanced that their full implications remain largely unexplored. They suggest that our three-dimensional universe might be embedded in a higher dimensional reality, governed by principles we are only beginning to glimpse. The suppression of these alternative theories by mainstream institutions represents more than scientific conservatism. It reflects deep-seated resistance to ideas that challenge fundamental assumptions about the nature of reality. The career incentives, funding structures, and publication systems that govern modern science all favor incremental research within established paradigms over revolutionary thinking that questions basic premises. This institutional bias has created what philosopher Thomas Kuhn called a paradigm lock, where scientific communities become so invested in particular theoretical frameworks that they resist evidence contradicting their foundational assumptions. The result is intellectual stagnation disguised as rigorous methodology. Graduate students learn quickly that questioning core assumptions about cosmic origins is professional suicide. They're trained to work within accepted frameworks, solving technical problems, and refining existing models rather than exploring genuinely alternative approaches. This educational system produces specialists who can manipulate complex equations but lack the conceptual flexibility to envision radically different scenarios. The peer review process, which should serve as quality control for scientific research, has become a barrier to revolutionary ideas. Reviewers who've built careers on Big Bang cosmology naturally resist approving papers that would invalidate their life's work, creating self-reinforcing cycles where only orthodox research receives support. This system violates the fundamental principles that should guide scientific inquiry. True science demands skepticism toward established theories, openness to new ideas, and willingness to abandon cherished concepts when evidence suggests they're incomplete or incorrect. The mathematical complexity of modern cosmological theories also serves as protective armor against criticism. The equations governing general relativity, quantum field theory, and inflationary cosmology are so intricate that only small communities of specialists can fully comprehend them. This technical barrier allows experts to dismiss external criticism while shielding their theories from broader scrutiny. Yet history shows that some of the most important scientific breakthroughs have come from outsiders who weren't constrained by conventional thinking. The amateur astronomers who first measured stellar parallax, the patent clerk who revolutionized physics, and the geologist who proposed continental drift all faced initial rejection from established experts who couldn't see beyond their assumptions. The current crisis in cosmology demands this kind of fresh perspective. We need researchers willing to question fundamental assumptions, explore alternative mechanisms, and follow evidence regardless of where it leads. We need institutions that support genuinely independent research rather than projects designed to confirm existing theories. The observational evidence supporting alternative cosmological models continues accumulating despite institutional resistance. Anomalous redshift phenomena, documented by numerous researchers, suggest that cosmic distances might differ fundamentally from standard assumptions. If redshift doesn't always indicate recession velocity, our entire cosmic distance scale becomes questionable. The quantized redshift observations that so troubled Holton Arp reveal patterns that would be extremely unlikely if redshift resulted purely from random recession velocities in an expanding universe. These patterns suggest that redshift might be intrinsic to objects themselves, related to their physical properties or evolutionary state, rather than their distance or motion. Recent observations with advanced telescopes continue revealing structures and phenomena that challenge Big Bang predictions. Massive galaxy clusters at high redshifts appear far too mature for their supposed age, suggesting either that structure formation occurred much more rapidly than theory predicts, or that these objects are actually much closer than their redshifts indicate. The discovery of vast cosmic voids containing virtually no galaxies presents another puzzle for standard cosmology. These empty regions are so large that light would barely have had time to cross them since the supposed beginning of the universe, yet they show clear boundaries and internal structure that suggest long evolutionary histories. Gravitational lensing observations sometimes reveal background objects that appear larger and brighter than the lensing models predict, hinting at distant scales that don't match redshift-based calculations. These anomalies accumulate like cracks in a theoretical foundation, suggesting fundamental flaws in our understanding of cosmic distances and evolution. The cosmic web's filamentary structure displays organization levels that seem impossible to achieve through random gravitational processes operating over Big Bang timescales. Computer simulations based on standard parameters can't reproduce the intricate patterns we observe, requiring constant adjustment of initial conditions and feedback mechanisms to match reality. Dark matter detection experiments continue failing to find the particles that supposedly comprise most of the universe's mass. Decades of searching with increasingly sensitive instruments have produced no confirmed detections, despite theoretical predictions that dark matter particles should be abundant and detectable. The lack of direct dark matter detection isn't just disappointing, it's becoming embarrassing for a theory that depends so heavily on this invisible component. If dark matter doesn't exist, then the entire theoretical framework of modern cosmology collapses, requiring complete reconstruction of our understanding of cosmic structure and evolution. Dark energy presents even greater challenges to our understanding. This mysterious force supposedly comprises nearly 70% of the universe's energy density, yet we have no idea what its actually leading candidate is. Alternative explanations for apparent cosmic acceleration don't require new forms of energy or modifications to known physics. Systematic effects in supernova observations, evolution of stellar properties over cosmic time, or local motion through inhomogeneous space could all mimic the signatures attributed to dark energy. The apparent acceleration might even result from our location in a cosmic void, where local expansion rates exceed the global average. If we occupy an underdense region of space, distant supernova would appear dimmer than expected in a homogeneous universe, creating the illusion of accelerated expansion. These alternative explanations are rarely discussed in mainstream cosmology because they challenge the theoretical framework that dominates the field. The scientific establishment has invested so heavily in the Big Bang paradigm that questioning its fundamental assumptions has become tantamount to heresy. But science isn't supposed to be a belief system protected from criticism. It's a method for discovering truth through observation, experimentation, and logical reasoning. When theories consistently fail to match observations, they should be questioned rather than rescued through increasingly elaborate modifications. The time has come to seriously consider whether we've been led astray by elegant mathematics that doesn't correspond to physical reality. The Big Bang theory might be a magnificent theoretical construction that tells us more about human psychology than about cosmic origins. Our desire for simple, comprehensible narratives about cosmic beginnings might have blinded us to evidence according to principles far suggesting that the universe operates stranger and more wonderful than we've imagined. Reality doesn't owe us explanations that fit our preconceptions or mathematical conveniences. The cosmos might be eternal rather than created, electric rather than gravitational, conscious rather than mechanical. These possibilities shouldn't frighten us, but inspire us with wonder at the magnificent complexity and mystery of existence. An eternal universe offers infinite time for cosmic evolution, allowing structures and processes to develop complexity beyond our current imagination. An electric cosmos suggests that consciousness and intelligence might be fundamental features of reality rather than accidental byproducts of material evolution. A conscious universe implies that our awareness and intelligence aren't isolated accidents in a hostile cosmos, but integral expressions of cosmic evolution itself. We might be the universe becoming aware of itself through billions of years of development and complexification. These ideas extend far beyond technical cosmology into the deepest questions about meaning, purpose, and our place in the grand scheme of existence. If the universe is eternal and conscious, then our lives take on significance that transcends individual mortality and connects us to cosmic processes spanning infinite time. The journey toward truth requires courage to question everything we've been taught, and openness to possibilities that extend far beyond current scientific consensus. The real universe, whatever its nature might be, is almost certainly stranger and more magnificent than anything we've yet dared to imagine. As we drift toward the conclusion of this cosmic exploration, remember that the questions we've raised tonight don't have easy answers. They require patient investigation, careful observation, and willingness to follow evidence wherever it leads, even when it challenges our most cherished beliefs about reality. The universe has been patiently waiting for minds brave enough to see beyond theoretical abstractions and mathematical constructions to glimpse the deeper reality that underlies all phenomena. That reality might be far more mysterious and wonderful than the Big Bang narrative suggests, offering insights into the nature of existence that could revolutionize human understanding. Tonight, as you prepare for sleep, let these ideas settle gently into your consciousness like cosmic dust gathering in the depths of space. Truth has a way of revealing itself to minds that remain open to possibilities beyond conventional wisdom. The cosmos continues its eternal dance around you, following principles that might be fundamentally different from everything you've been taught to believe. In questioning these established narratives, you join a long tradition of seekers who've dared to look beyond comfortable certainties toward deeper truths about the nature of existence itself. Sweet dreams, fellow traveler in this magnificent cosmic mystery. The universe keeps its secrets well, but patient investigation and fearless questioning might eventually unlock doors to understanding that have remained closed for far too long. The mathematical foundations upon which the Big Bang theory rests begin to crumble when we examine them with fresh eyes, unencumbered by decades of theoretical conditioning. What we discover is a house of cards built upon assumptions so fundamental that questioning them feels like challenging reality itself. Yet this is precisely what honest scientific inquiry demands. Consider the Hubble constant, that crucial number that supposedly tells us how fast the universe is expanding. This single parameter underpins our entire cosmic timeline, determining the age of the universe and the distance to every object beyond our local galactic neighborhood. Yet measurements of the Hubble constant produce values that differ significantly depending on the method used. Local measurements using nearby supernovae and Cepheid variable stars yield one value, while observations of the cosmic microwave background produce another. This isn't a minor discrepancy that can be resolved with better instruments. The difference represents a fundamental crisis that cosmologists have dubbed the Hubble tension, a polite term for what amounts to a complete breakdown in our understanding of cosmic expansion. The standard response involves invoking new physics, proposing modifications to the expansion history, or suggesting that unknown systematic errors plague one or both measurement methods. But what if the problem runs deeper? What if the entire concept of uniform cosmic expansion is fundamentally flawed? The assumption that the universe expands uniformly in all directions seems reasonable from our limited earthbound perspective, but it's never been independently verified. We observe redshift and assume it indicates recession velocity, then use this assumption to construct models of cosmic expansion that that we never question. The circular reasoning becomes apparent once you step outside the theoretical framework. Regional variations in expansion rates could easily explain the Hubble tension without requiring exotic new physics or systematic measurement errors. If we happen to live in a region of space where expansion occurs faster or slower than the cosmic average, then our local measurements would naturally disagree with global estimates derived from the cosmic microwave background. This possibility isn't seriously considered because it challenges the fundamental assumption of cosmic homogeneity upon which modern cosmology depends. The COP, which states Ernican principle, that we don't occupy a special location in the universe, has been elevated from a useful working assumption to an unquestionable dogma. But what if we do occupy a special location? What if the observable universe around us isn't representative of the cosmos as a whole? The very fact that we exist suggests that our location might be atypical, since the vast majority of space appears to be empty and lifeless. The fine structure constant, which governs the strength of electromagnetic interactions another window, provides into the assumptions underlying modern cosmology. This dimensionless number appears to be constant throughout our local region of space and time, but observations of distant quasars hint at possible variations that could revolutionize our understanding of physical law. If fundamental constants change over cosmic distances or timescales, then our interpretation of distant observations requires complete revision. The light from ancient quasars and we receive distant galaxies would be subtly modified by these variations, creating apparent recession velocities that don't correspond to actual motion through space. Such variations would naturally explain the quantized redshift phenomena that so troubled Holton Arp and other observational astronomers. Instead of representing intrinsic properties of distant objects, these redshift patterns could reflect the evolution of physical constants over time cosmic history, or their variation with distance from our location. The implications extend far beyond cosmology into the foundations of physics itself. If constants aren't actually constant, then the laws of nature might be more fluid and dynamic than we've assumed. The universe could be continuously experimenting with different parameter values, exploring the space of possible physical realities over vast timescales. This dynamic view of physical law eliminates many of the fine-tuning problems that plague standard cosmology. Instead of requiring incredible coincidences to explain why the universe's properties permit complexity and life, we can invoke evolutionary processes that gradually optimize physical parameters for structure formation and biological development. The anthropic principle, which suggests that we observe the physical constants we do because only universes with these values can produce observers, becomes unnecessary in a cosmos where constants evolve naturally toward life-supporting values. The apparent design in nature reflects not supernatural intervention, but natural selection operating at cosmic scales. Plasma physics offers profound insights into cosmic evolution that remain largely ignored by mainstream astronomy. Laboratory experiments routinely produce scaled versions of cosmic phenomena, from spiral galaxy structures to stellar formation processes, using nothing more exotic than ionized gas and magnetic fields. The scalability of plasma phenomena represents one of its most remarkable features. The same equations that govern laboratory discharges also describe the behavior of interstellar and intergalactic plasma over distances spanning many orders of magnitude. This universality suggests that electromagnetic forces play a much larger role in cosmic evolution than gravitational models acknowledge. Birkeland currents, named after the Norwegian physicist who first studied them, consist of field-aligned electrical currents flowing through plasma along magnetic field lines. These currents can persist over enormous distances, transporting energy and matter across cosmic scales with remarkable efficiency. The filamentary structure of the cosmic web bears striking resemblance to the patterns created by Birkeland currents in laboratory plasma experiments. The magnetic fields threading space naturally channel ionized matter into the web-like architecture we observe, eliminating the need for exotic dark matter to provide gravitational scaffolding. Galaxy formation becomes a natural consequence of electromagnetic pinch effects that compress plasma along current-carrying filaments. These same forces shape stellar formation within galaxies, creating the periodic structures and unexpected chemical abundances that puzzle conventional astronomers. The jets streaming from active galactic nuclei represent perhaps the most dramatic manifestation of cosmic electromagnetic phenomena. These highly collimated beams of matter and energy extend for hundreds of thousands of light-years while maintaining their focus and stability, a feat that purely gravitational models struggle to explain. Electromagnetic acceleration mechanisms naturally produce the observed jet properties without requiring supermassive black holes or exotic physics. The magnetic fields threading galactic cores can accelerate charged particles to relativistic velocities while maintaining beam collimation through self-focusing effects inherent in current-carrying plasma. Variable star phenomena, from the regular pulsations of Cepheids to the explosive outbursts of novae and supernovae, might reflect electromagnetic rather than purely nuclear processes. Electrical discharges between stellar surfaces and surrounding plasma sheaths could explain the periodicity and energy release observed in these cosmic lighthouses. Even planetary formation might involve electromagnetic forces more than gravitational accretion. The electric fields associated with young stars could sort matter by charge and composition, explaining the observed chemical gradients in planetary systems and the unexpected properties of exoplanets that continue to surprise astronomers. The electromagnetic paradigm eliminates the need for most of the exotic components that populate standard cosmological models. Dark matter, dark energy, inflation, and other theoretical constructs become unnecessary when electromagnetic forces are properly incorporated into cosmic evolution scenarios. This doesn't mean that gravity becomes irrelevant, but rather that it operates within a cosmic environment dominated by electromagnetic phenomena. The interplay between gravitational and electromagnetic forces creates the rich variety of structures and behaviors we observe throughout the universe. The resistance to electromagnetic cosmology within academic institutions reflects more than scientific conservatism. It represents a fundamental challenge to the reductionist worldview that has dominated physics since the early 20th century. Electromagnetic theories suggest that the cosmos, than a mechanical, operates more like a living organism clockwork. This organic view of cosmic evolution implies that consciousness and intelligence might emerge naturally from the complex electromagnetic processes that shape cosmic structure. Instead of being accidental byproducts of chemical evolution, awareness and information processing could be fundamental features of reality itself. The bioelectric phenomena underlying consciousness operate according to the same electromagnetic principles that govern cosmic plasma. The human nervous system generates complex field patterns that somehow give rise to thoughts, emotions, and self-awareness through mechanisms we're only beginning to understand. If similar electromagnetic processes occur throughout the cosmos, then consciousness might be a universal phenomenon that manifests at every scale of organization. The intricate field patterns threading galaxies and galaxy clusters could represent forms of cosmic awareness that dwarf human intelligence while operating according to recognizable principles. This possibility transforms our understanding of humanity's place in the universe. Instead of being isolated accidents in a hostile cosmos, we become integral components of a conscious universe that has been developing awareness and intelligence for timescales beyond human comprehension. The implications reach into every aspect of human experience, from our understanding of individual consciousness to our collective relationship with the natural world. If consciousness is fundamental to cosmic evolution, then our awareness represents not an emergent property of complex chemistry, but a direct participation in universal processes. The suppression of these ideas within academic institutions reflects deep-seated resistance to concepts that challenge materialist assumptions about the nature of reality. The possibility that consciousness might be fundamental rather than emergent threatens theoretical frameworks that have dominated scientific thinking for generations. Yet the evidence continues accumulating despite institutional resistance. Advances in neuroscience reveal the electromagnetic basis of consciousness, while astronomical observations discover electromagnetic phenomena throughout space that operate according to principles we can study in laboratory settings. The convergence of these research streams suggests that a new synthesis might be emerging, one that recognizes consciousness as a fundamental feature of cosmic evolution rather than an accidental byproduct of material complexity. This synthesis could revolutionize not only our understanding of the universe, but our comprehension of what it means to be human. Steady-state cosmology offers another pathway beyond the limitations of Big Bang thinking, proposing mechanisms for continuous creation that don't violate known physics while eliminating the need for absolute beginnings. The quantum vacuum, far from being empty space, teems with virtual particles that briefly materialize before vanishing back into the void. Under certain conditions, these quantum fluctuations might become permanent additions to the material universe. The process would occur so gradually that it would be undetectable by current instruments, yet over cosmic timescales it could account for the matter and energy we observe without requiring a singular moment of creation. This continuous creation wouldn't violate conservation laws because the total energy of the universe, including gravitational potential energy, might always sum to zero. The positive energy of matter and radiation would be exactly balanced by the negative gravitational potential energy of cosmic structure, maintaining perfect conservation while allowing for ongoing creation. The philosophical implications of continuous creation extend far beyond technical cosmology. An eternally creative universe suggests that novelty and emergence are fundamental features of reality rather than temporary departures from equilibrium states that must eventually decay toward maximum entropy. This creative cosmos implies that evolution operates at every scale, from quantum fluctuations to galactic clusters, continuously generating new forms of organization and complexity. The universe doesn't wind down like a cosmic clock, but winds up toward ever greater sophistication and awareness. The biological implications are particularly profound. If continuous creation operates throughout space and time, then the emergence of life and consciousness represents not an improbable accident, but a natural expression of cosmic creativity. The universe might be inherently biophilic, favoring the development of living systems and conscious observers. This perspective dissolves the artificial boundary between living and non-living matter, suggesting instead a spectrum of organization and awareness that extends from quantum fields to cosmic structures. Life becomes a natural phase transition in the evolution of matter and energy toward greater complexity and consciousness. The resistance to steady-state cosmology within academic institutions reflects not only theoretical conservatism, but existential anxiety about a universe without clear beginnings or endings. The Big Bang narrative provides psychological comfort by offering a definite origin story that parallels religious creation myths. But psychological comfort isn't scientific truth, and the evidence increasingly suggests that reality operates according to principles far stranger and more wonderful than our creation myths suggest. An eternal universe with continuous creativity offers infinite opportunities for growth, development, and discovery that dwarf any finite cosmology. The observational evidence supporting alternative cosmologies continues accumulating, despite institutional resistance and theoretical prejudice. Each new discovery seems to reveal phenomena that challenge Big Bang predictions while supporting models based on electromagnetic forces, continuous creation, or cyclic evolution. The time has come for a fundamental reassessment of our cosmological assumptions. This doesn't mean abandoning scientific rigor or embracing speculation disguised as fact. It means returning to the basic principles of scientific inquiry: careful observation, logical reasoning, and willingness to follow evidence regardless of where it leads. The universe has been patiently revealing its secrets to anyone willing to look beyond theoretical preconceptions and mathematical abstractions. What we're discovering suggests a cosmos far more ancient, mysterious, and magnificent than the Big Bang narrative allows. This cosmic reality operates according to principles that might be fundamentally different from everything we've been taught to believe. Electromagnetic forces shape galactic evolution, consciousness emerges naturally from complex field interactions, and continuous creation maintains cosmic vitality across infinite time. These aren't just abstract theoretical possibilities, but potentially observable phenomena that could transform human understanding if given fair consideration. The suppression of alternative ideas within academic institutions has delayed this transformation, but truth has a way of emerging despite institutional resistance. As we approach the conclusion of this exploration, remember that questioning established dogma represents not rebellion against science, but a return to its fundamental values. True scientific inquiry demands skepticism toward accepted theories, openness to new possibilities, and courage to follow evidence into uncharted territory. The cosmos continues its eternal dance around us, following principles that might be radically different from current scientific consensus. In recognizing this possibility, we open ourselves to discoveries that could revolutionize human understanding and reveal our true place in the magnificent mystery of existence. The journey toward truth requires patience, courage, and willingness to abandon comfortable certainties when evidence demands revision. The real universe, whatever its nature might be, deserves our best efforts to understand it honestly, rather than forcing it to conform to theoretical preconceptions. Tonight, as consciousness settles into the gentle rhythms of approaching sleep, let these ideas drift through your awareness like cosmic dust gathering in the depths of space. Truth reveals itself to minds that remain open to possibilities beyond conventional wisdom, patient observers willing to see beyond the boundaries of accepted knowledge. The universe keeps its deepest secrets well hidden, but persistent inquiry and fearless questioning might eventually unlock understanding that has remained closed for far too long. In this quest for cosmic truth, we join countless generations of seekers who've dared to look beyond comfortable assumptions toward the deeper mysteries that surround and sustain all existence. The cosmic deception runs even deeper than most people realize, extending into the very mathematical foundations that cosmologists claim validate their theories. When we peer beneath the elegant equations and sophisticated models, we discover a framework built upon assumptions so questionable that maintaining them requires increasingly desperate intellectual gymnastics. Take the concept of cosmic inflation, that theoretical period of exponential expansion supposedly occurring in the first fraction of a second after the Big Bang. This mechanism was invented specifically to solve problems with the standard model, yet it creates far more puzzles than it resolves. The inflationary epoch requires field energies so enormous that they dwarf anything we observe in the contemporary universe by factors that stretch credibility beyond breaking point. The inflaton field, The hypothetical quantum field driving this expansion must possess properties that seem almost magical. It needs to maintain nearly constant energy density while the universe expands by factors of 10 to the 60th power or more. This field must then decay at precisely the right moment, transferring its energy to ordinary matter and radiation with exquisite timing that permits structure formation. The fine-tuning required for successful inflation exceeds the problems it was designed to solve. The initial conditions must be set with precision that makes balancing a needle on its point for eternity seem trivial by comparison. Any slight deviation from these perfect parameters would produce a universe that either collapses immediately or expands so rapidly that matter never condenses into stars and galaxies. Cosmologists respond to these challenges by proposing eternal inflation, where our universe becomes one bubble in an infinite foam of expanding regions. This multiverse scenario supposedly eliminates fine-tuning by allowing all possible parameters to be realized somewhere. Yet this solution creates new problems that dwarf the original difficulties. If eternal inflation is correct, then everything we observe becomes infinitely improbable. Our particular arrangement of galaxies, stars, and planets should be overwhelmingly unlikely compared to simpler configurations that achieve the same observational consequences. The theory predicts that we should observe ourselves as isolated brains floating in empty space rather than complex biological organisms on a planet orbiting a star. This measure problem, as cosmologists euphemistically term it, represents a complete breakdown of predictive power. A theory that can explain any possible observation while making no definite predictions about what we should actually see has abandoned the fundamental requirements of scientific methodology. It becomes unfalsifiable metaphysics disguised as empirical science. The cosmic microwave background observations that supposedly confirm inflation actually raise profound questions about the theory's viability. The temperature fluctuations we observe are remarkably Gaussian, meaning they follow the statistical distribution expected from random quantum processes. Yet, inflation predicts significant non-Gaussian signatures that should be easily detectable with current instruments. The absence of these predicted features forces theorists to invoke increasingly contrived models where the inflaton field behaves in precisely the manner needed to eliminate observable consequences. The theory becomes so flexible that it can accommodate any observation by adjusting parameters, violating the principle that genuine scientific theories should make risky predictions that could potentially falsify them. Primordial gravitational waves represent another testing ground where inflation consistently fails to deliver promised evidence. These ripples in space-time should have been generated during the inflationary epoch and remain detectable today as distinctive polarization patterns in the cosmic microwave background. Despite decades of searching with increasingly sensitive instruments, no confirmed detection has emerged. The continued absence of primordial gravitational waves doesn't lead to questioning inflation, but to lowering the predicted amplitude until it falls below current detection thresholds. The theory adapts to preserve itself rather than making bold predictions that could definitively confirm or refute its validity. This adaptive behavior reveals the unfalsifiable nature that characterizes much of modern cosmological thinking. Dark matter detection experiments provide another window into the theoretical crisis plaguing contemporary cosmology. These sophisticated underground laboratories, buried deep beneath mountains to shield them from cosmic rays and other background interference, have been searching for dark matter particles for more than 3 decades without success. The latest generation of detectors can identify individual atomic nuclei recoiling from collisions with hypothetical dark matter particles. These instruments achieve sensitivity levels that should have detected the most popular dark matter candidates years ago, yet they consistently produce null results that force theorists to invoke increasingly exotic particle properties. Weakly interacting massive particles, or WIMPs, were once the leading candidates for dark matter. These hypothetical particles should interact with ordinary matter through the weak nuclear force, making them detectable in underground experiments while remaining invisible to electromagnetic radiation. The failure to detect WIMPs after exhaustive searching has largely eliminated this entire class of candidates. Axions, ultralight particles that barely interact with ordinary matter, represent the current favorite among theorists seeking to preserve dark matter's existence. These hypothetical particles would be produced in stellar cores and pervade the galaxy in sufficient quantities to account for the missing mass inferred from galactic rotation curves. Yet axion searches using resonant cavities and magnetic field interactions have similarly produced no confirmed detections. The continued failure of direct detection experiments doesn't lead to questioning whether dark matter exists, but to proposing ever more exotic particles with interaction cross-sections so small they approach the boundaries of what could ever be measured. The theory evolves to remain forever just beyond experimental reach while maintaining the illusion of testability. Modified gravity theories offer compelling alternatives that eliminate dark matter entirely, while explaining galactic rotation curves through changes to gravitational physics at cosmic scales. These theories propose that Newton's inverse square law breaks down over distances comparable to galactic radii, producing apparent dark matter effects through purely gravitational mechanisms. MOND, or Modified Newtonian Dynamics, successfully predicts rotation curves for hundreds of galaxies using a single adjustable parameter related to the acceleration scale where modifications become important. This theory's success rate far exceeds that of dark matter models, which require individual mass distributions fitted separately for each galaxy to match observations. Emergent gravity theories suggest that gravitational attraction might arise from more fundamental interactions that behave differently at cosmic scales. These approaches treat gravity as an entropic force emerging from the statistical behavior of information encoded on cosmic horizons, naturally producing modifications that mimic dark matter effects. The resistance to modified gravity within academic institutions reveals the theoretical prejudice that pervades modern cosmology. Instead of seriously investigating alternatives that could eliminate the need for invisible matter, researchers prefer to invoke increasingly exotic particles that may never be detected. This preference reflects career incentives and funding structures that reward conformity over revolutionary thinking. Plasma cosmology offers profound insights into cosmic structure formation that remain systematically ignored by mainstream astronomy. The electromagnetic forces governing plasma behavior operate according to well-understood principles that can be studied in laboratory settings and scaled to cosmic dimensions with remarkable consistency. The cosmic web's filamentary architecture directly parallels the structures produced by electrical discharges in plasma physics experiments. These laboratory demonstrations reveal how electromagnetic forces naturally create the network of filaments and voids we observe throughout space without requiring dark matter scaffolding or exotic physics. Galaxy formation becomes a natural consequence of electromagnetic pinch effects that concentrate plasma along current-carrying filaments. The same forces that create lightning bolts and aurora displays shape galactic structure on scales spanning hundreds of thousands of light years. These electromagnetic processes operate far more efficiently than gravitational collapse in creating the rapid structure formation we observe. Stellar formation within galaxies follows similar electromagnetic principles, with plasma currents channeling matter into the dense concentrations necessary for nuclear ignition. The unexpected abundance of heavy elements in supposedly young stars becomes comprehensible when electromagnetic sorting processes preferentially concentrate metallic ions during stellar assembly. Active galactic nuclei, those incredibly energetic objects that outshine entire galaxies, represent electromagnetic phenomena rather than gravitational engines powered by supermassive black holes. The jets streaming from these objects follow magnetic field lines across intergalactic distances, maintaining their collimation through self-focusing effects inherent in current-carrying plasma. The periodic variability observed in quasars and other active nuclei reflects the oscillatory behavior characteristic of electrical discharge phenomena rather than the chaotic accretion processes predicted by gravitational models. These electromagnetic explanations eliminate the need for impossible energy densities and exotic physics while providing natural mechanisms for the observed behaviors. Redshift quantization represents perhaps the most devastating challenge to expansion cosmology, yet it remains largely ignored by mainstream institutions despite compelling observational evidence. Multiple independent researchers have documented cases where galactic redshifts cluster around specific values that would be extremely unlikely if redshift resulted from random recession velocities. William Tift's pioneering studies revealed periodicity in galactic redshifts that suggests intrinsic rather than cosmological origins for this phenomenon. His careful analysis of galaxy pairs and groups showed redshift differences that cluster around multiples of approximately 72 kilometers per second, a pattern that expansion cosmology cannot easily accommodate. Holt and Arp extended these investigations to include active galactic nuclei and quasars, discovering numerous cases where objects with dramatically different redshifts appear physically connected by bridges of matter or show clear gravitational interactions. According to standard cosmology, these objects should be separated by billions of light years, making such connections impossible. The systematic dismissal of quantized redshift observations reveals the institutional bias that protects expansion cosmology from legitimate criticism. Rather than investigating these anomalies or attempting to replicate the observations, the astronomical community marginalized researchers who reported contrary evidence while denying them access to major telescopes. This suppression of inconvenient data violates fundamental principles of scientific methodology that should govern empirical investigation. The proper response to anomalous observations involves careful replication and analysis rather than dismissal based on theoretical preconceptions. The failure to follow these basic procedures suggests that cosmology has abandoned scientific rigor in favor of dogmatic adherence to preferred theories. Variable fundamental constants offer another pathway beyond the limitations of current cosmological thinking. If the strength of electromagnetic interactions, the masses of fundamental particles, or other basic parameters change over cosmic time or distance, then our interpretation of distant observations requires complete revision. Recent observations of distant quasars using the world's largest telescopes hint at possible variations in the fine structure constant over cosmic epochs. These subtle changes would modify the light we receive from ancient objects in ways that could mimic expansion redshift, while actually reflecting the evolution of physical law itself. Such variations would naturally explain the apparent fine-tuning of physical constants without requiring multiverse scenarios or anthropic arguments. Instead of incredible coincidences that permit complexity and life, we could invoke evolutionary processes that optimize physical parameters over cosmic timescales, through mechanisms we're only beginning to understand. The implications extend far beyond cosmology into the foundations of physics itself. If constants aren't actually constant, then the laws of nature might be more dynamic and adaptive than we've assumed. The universe could be continuously exploring the space of possible physical realities, naturally evolving toward configurations that support structure formation and biological development. This evolutionary view of physical law eliminates many paradoxes that plague contemporary physics, while opening new avenues for understanding cosmic development. Instead of being fixed features imposed from outside, the laws of nature become emergent properties of cosmic evolution that develop naturally through processes operating over vast timescales. The bioelectric foundations of consciousness provide compelling evidence for the electromagnetic basis of awareness and intelligence throughout the cosmos. The human nervous system operates as a sophisticated electromagnetic system that generates complex field patterns, somehow giving rise to thoughts, emotions, and self-awareness through mechanisms we're only beginning to comprehend. If consciousness emerges from electromagnetic field interactions in biological systems, then similar processes might occur throughout the cosmos wherever complex electromagnetic phenomena develop sufficient organization and integration. The intricate magnetic field structures threading galaxies and galaxy clusters could represent forms of cosmic awareness operating on scales that dwarf human intelligence. This possibility transforms our understanding of humanity's place in the universe from isolated accidents in a hostile cosmos to integral components of a conscious universe, developing awareness and intelligence over timescales beyond human comprehension. Our individual consciousness becomes a local manifestation of universal processes rather than an emergent property of chemical complexity. The suppression of consciousness research within academic institutions reflects deep-seated resistance to ideas that challenge materialist assumptions about the nature of mind and reality. The possibility that consciousness might be fundamental rather than emergent threatens theoretical frameworks that have dominated scientific thinking since the early 20th century. Yet advances in neuroscience continue revealing the electromagnetic basis of neural function, while astronomical observations discover electromagnetic phenomena throughout space operating according to principles we can study in laboratory settings. The convergence of these research streams suggests that a new synthesis might be emerging that recognizes consciousness as a fundamental feature of cosmic evolution. Continuous creation mechanisms offer elegant solutions to cosmic evolution without requiring absolute beginnings or violating known physics. The quantum before vanishing back into the void, vacuum teams with virtual particles that briefly materialize yet under certain conditions. These fluctuations might become permanent additions to the material universe. This process would occur so gradually that current instruments couldn't detect it, requiring only the appearance of a single hydrogen atom per cubic meter of space every few billion years to maintain cosmic density during expansion. The mechanism violates no conservation laws because the total energy of the universe, including gravitational potential energy, might always sum to zero. The positive energy of matter and radiation would be exactly balanced by negative gravitational potential energy of cosmic structure, maintaining perfect conservation while allowing ongoing creation. This steady-state approach eliminates the initial conditions problem while providing infinite time for cosmic evolution to develop the complex structures we observe. The philosophical implications of continuous creation extend far beyond technical cosmology into our understanding of novelty, creativity, and purpose in cosmic evolution. An eternally creative universe suggests that emergence and development are fundamental features of reality rather than temporary departures from equilibrium states that must eventually decay. This creative cosmos implies that evolution operates at every scale, from quantum fluctuations to galactic clusters, continuously generating new forms of organization and complexity. The universe doesn't wind down like a mechanical clock, but winds up toward ever greater sophistication and awareness through processes that operate indefinitely. The biological implications are particularly profound, suggesting that life and consciousness represent natural expressions of cosmic creativity rather than improbable accidents requiring incredible fine-tuning. The universe might be inherently biophilic, favoring the development of living systems and conscious observers through mechanisms built into its fundamental structure. As we approach the culmination of this exploration, the evidence overwhelmingly suggests that we've been systematically misled about the most fundamental questions concerning cosmic origins and evolution. The Big Bang Theory, despite its mathematical elegance and widespread acceptance, fails to address numerous observational challenges while requiring increasingly exotic components to maintain theoretical consistency. Alternative approaches based on electromagnetic forces, continuous creation, or cyclic evolution offer compelling explanations for cosmic phenomena without invoking invisible matter, mysterious energy, or impossible initial conditions. These theories operate according to principles we can study directly while providing natural mechanisms for the complex structures and behaviors we observe throughout space. The institutional suppression of these alternatives represents more than scientific conservatism. It reflects systematic resistance to ideas that challenge fundamental assumptions about the nature of reality itself. The career incentives, funding structures, and publication systems governing modern science all favor incremental research within established paradigms over revolutionary thinking that questions basic premises. This institutional bias has created what amounts to a cosmological orthodoxy that protects cherished theories from legitimate criticism while silencing dissenting voices. The result is intellectual stagnation disguised as rigorous methodology, where conformity to established doctrine becomes more important than empirical truth. The time has come for a fundamental reassessment of our cosmological assumptions based on careful observation rather than theoretical prejudice. This doesn't mean abandoning scientific rigor, but returning to the basic principles of empirical investigation, following evidence wherever it leads regardless of how much it challenges accepted beliefs. The universe continues revealing its secrets to anyone willing to look beyond mathematical abstractions and theoretical constructions. What we're discovering suggests a cosmos far more ancient, mysterious, and magnificent than current scientific consensus allows, operating according to principles that might be fundamentally different from everything we've been taught. The journey toward cosmic truth requires courage to question established authority and patience to investigate alternatives that extend beyond comfortable certainties. The real universe, whatever its nature might be, deserves our best efforts to understand it honestly, rather than forcing observations to conform to preferred theoretical frameworks. In recognizing these possibilities, we open ourselves to discoveries that could revolutionize human understanding while revealing our true place in the magnificent mystery of existence. The cosmos has been patiently waiting for minds brave enough to see beyond conventional wisdom toward the deeper truths that surround and sustain all reality. Tonight, as we stand at the threshold of understanding, we must confront an uncomfortable truth that stretches beyond the realm of astronomy and touches the very foundations of human knowledge itself. What if the greatest deception isn't just about cosmic origins, but about the nature of reality and our ability to perceive it accurately? The electromagnetic universe that plasma cosmologists describe operates according to principles that extend far beyond galactic structure and stellar formation. These same electromagnetic forces that shape cosmic architecture also govern the most intimate processes of biological existence, creating an unbroken chain of connection between the largest and smallest scales of reality. Consider the extraordinary synchronization we observe throughout nature, from the quantum coherence that enables photosynthesis to the precise timing of biological rhythms that govern cellular function. These phenomena suggest that electromagnetic fields carry information across vast distances instantaneously, coordinating biological processes through mechanisms that transcend our current understanding of space and time. The morphic resonance proposed by biologist Rupert Sheldrake offers a compelling explanation for how information propagates throughout living systems without requiring physical transmission. If electromagnetic fields can store and transmit complex patterns of organization, then the memories and behaviors of organisms could be shared across generations through field interactions rather than purely genetic mechanisms. This field-based inheritance would operate according to the same principles that govern cosmic plasma, suggesting that consciousness and memory might be distributed properties of electromagnetic fields rather than localized phenomena confined to individual brains. The implications for human potential and collective awareness are staggering. The suppression of morphic resonance research within academic institutions parallels the marginalization of plasma cosmology, revealing a systematic bias against theories that challenge mechanistic assumptions about biological and cosmic evolution. Both fields of inquiry threaten established paradigms by proposing that information and organization emerge through field interactions rather than purely material processes. The healing effects observed in various forms of energy medicine become comprehensible when we recognize that biological systems operate as sophisticated electromagnetic networks. The acupuncture meridians mapped by traditional Chinese medicine correspond remarkably well to the electromagnetic field patterns that govern cellular communication and tissue organization. Homeopathic remedies, dismissed by conventional medicine as impossible placebo effects, might actually work through electromagnetic information transfer that occurs below the threshold of chemical detection. The water memory experiments conducted by Jacques Bonveniste suggest that electromagnetic field patterns can be stored and transmitted through aqueous solutions, providing a physical mechanism for homeopathic action. The systematic suppression of energy medicine research reveals the same institutional bias that protects cosmological orthodoxy from legitimate challenge. Studies demonstrating therapeutic effects from electromagnetic field interventions are routinely rejected by medical journals, not because of methodological flaws, but because they contradict materialist assumptions about biological function. This rejection of electromagnetic explanations extends into consciousness research, where the hard problem of consciousness remains unsolved, precisely because neuroscientists refuse to consider field-based models of awareness. The electromagnetic field patterns generated by neural networks might represent the actual byproducts of chemical substrate of consciousness, rather than mere activity. Near-death experiences, remote viewing phenomena, and other anomalous consciousness effects become natural consequences of field-based awareness, rather than impossible violations of physical law. If consciousness operates through electromagnetic fields that extend beyond the boundaries of individual brains, then these phenomena represent normal expressions of human potential rather than supernatural anomalies. The Global Consciousness Project, which monitors random number generators worldwide for correlations during major events, has documented statistically significant deviations that suggest collective human consciousness can influence physical processes through electromagnetic field interactions. These findings imply that human awareness participates directly in cosmic evolution rather than merely observing it from outside. The resistance to consciousness research within academic institutions reflects the same pattern of suppression that characterizes cosmological and biological fields. Researchers who investigate anomalous phenomena find their careers threatened, their funding eliminated, and their publications rejected by mainstream journals that refuse to consider evidence challenging materialist orthodoxy. This institutional capture extends beyond individual scientific disciplines into the very structure of knowledge production itself. The peer review process, grant funding mechanisms, and academic promotion systems all favor research that confirms established paradigms while systematically excluding investigations that might revolutionize our understanding of reality. The corporate funding of scientific research creates additional layers of bias that protect profitable theories from challenge, while suppressing discoveries that might threaten existing economic interests. Pharmaceutical companies have little incentive to support energy medicine research that could eliminate the need for expensive drug interventions, just as energy corporations resist technologies that might provide unlimited clean power. The military-industrial complex plays a particularly insidious role in suppressing revolutionary discoveries, classifying breakthrough technologies under national security provisions while preventing their beneficial application for civilian purposes. The secrecy surrounding anti-gravity research, zero-point energy extraction, and consciousness-based technologies suggests that far more advanced understanding exists than publicly acknowledged. Whistleblower testimonies from former military and intelligence personnel describe programs that have successfully developed technologies based on principles that contradict publicly accepted physics. These testimonies, dismissed by mainstream science as delusional fantasies, might actually reveal the existence of a parallel scientific establishment that operates beyond public scrutiny. The UFO phenomenon, recently acknowledged by government agencies after decades of denial, provides compelling evidence for technologies that transcend current theoretical limitations. The observed flight characteristics of unidentified aerial phenomena suggest propulsion systems that manipulate electromagnetic fields or space-time geometry in ways that conventional physics claims are impossible. Whether these technologies represent human developments or non-human intelligence, their existence demonstrates that our publicly acknowledged understanding of physical law is woefully incomplete. The systematic suppression of UFO research over decades reveals the lengths to which institutional authority will go to protect established paradigms from challenging evidence. The disclosure process currently unfolding might represent the beginning of a broader revelation that could transform human civilization. If the technologies demonstrated by UFOs become publicly available, they would revolutionize energy production, transportation, and communication, while validating alternative theories that have been marginalized for generations. The free energy devices that inventors have claimed to develop, only to have their patents suppressed and their lives threatened, might actually represent legitimate discoveries based on electromagnetic principles that challenge the scarcity-based economic system. The suppression of these technologies maintains artificial energy dependence while preventing the abundance that could eliminate poverty and environmental destruction. The water-powered engines, over-unity electromagnetic generators, and other anomalous energy devices documented by researchers like Eugene Malov and Stephen Greer suggest that the universe operates according to principles that make unlimited clean energy readily available. The systematic suppression of these technologies reveals the economic and political interests that benefit from maintaining artificial scarcity. The cold fusion controversy exemplifies the institutional bias against discoveries that threaten established interests. The Pons-Fleischmann experiments, demonstrating nuclear reactions at room temperature, were systematically discredited by the physics establishment, despite successful replications by researchers worldwide. The suppression of cold fusion research has delayed the development of clean, abundant energy for decades. Recent developments in low-energy nuclear reactions have vindicated the original cold fusion claims while revealing electromagnetic mechanisms for nuclear transmutation that operate outside the high-energy paradigm of conventional physics. These discoveries suggest that nuclear processes can be triggered and controlled through electromagnetic field manipulations, rather than requiring massive particle accelerators or fusion reactors. The biological transmutations observed by Louis Kervran and other researchers demonstrate that living systems routinely accomplish nuclear transformations through enzymatic processes that conventional physics claims are impossible. These biological nuclear reactions operate at body temperature and pressure, suggesting that life itself has mastered technologies that human science has barely begun to understand. The alchemical traditions that dominated early chemistry might have preserved knowledge of electromagnetic transmutation processes that were later suppressed by mechanistic science. The symbolic language of alchemy could encode practical techniques for manipulating matter through field interactions rather than purely chemical transformations. The sacred geometry patterns found in ancient monuments worldwide might represent technological blueprints for electromagnetic devices rather than merely decorative or religious symbols. The precise mathematical relationships encoded in structures like the Great Pyramid suggest that ancient civilizations possessed advanced understanding of field physics that has been lost to modern science. The megalithic structures scattered continent demonstrated across every construction techniques that challenge conventional archaeology, while suggesting technologies based on electromagnetic levitation and matter manipulation. The precision of these monuments exceeds what should be possible with primitive tools, implying access to principles of physics that our current science hasn't rediscovered. The suppression of alternative archaeology parallels the marginalization of alternative cosmology, revealing systematic resistance to evidence that challenges established historical narratives. Discoveries that suggest advanced ancient technologies are routinely dismissed or ignored by academic institutions that prefer simple progression models of human development. The Antikythera mechanism, discovered in a shipwreck dating to ancient Greece, demonstrates computational sophistication that shouldn't have existed for another 1,000 years according to conventional historical timelines. This device suggests that technological development doesn't follow the linear progression assumed by mainstream archaeology. The precision machining evident in ancient Egyptian granite artifacts implies access to tools and techniques that surpass modern capabilities in some respects. The perfectly smooth surfaces and precise angles achieved in these objects suggest technologies based on electromagnetic field manipulation rather than mechanical cutting and grinding. Tonight, as you prepare for sleep, perhaps feeling the gentle pull of these ideas settling into your consciousness, remember that questioning isn't just about challenging what we've been told. It's about embracing the possibility that reality might be far stranger and more magnificent than we ever dared imagine. The evidence we've explored together suggests that the universe operates according to principles that extend far beyond the comfortable boundaries of current scientific consensus. Whether it's the electromagnetic forces shaping cosmic architecture, the continuous creation maintaining eternal vitality, or the conscious awareness emerging from field interactions throughout space, we find ourselves part of something infinitely more mysterious and wonderful than the Big Bang narrative allows. The suppression of these alternative perspectives reveals something profound about human nature itself. we tend to protect our beliefs even when evidence suggests they might be incomplete. But in that protection, we might be missing the most extraordinary discoveries about the nature of existence itself. Sweet dreams, fellow traveler in this cosmic mystery. The universe continues its eternal dance around you, following principles that might be fundamentally different from everything you've learned. In questioning these established narratives, you've joined a tradition of seekers brave enough to look beyond comfortable certainties toward deeper truths about reality itself. The cosmos keeps its secrets well, but patient investigation and fearless questioning might eventually unlock understanding that transforms not just our knowledge of the universe, but our comprehension of what it means to be conscious beings participating in this magnificent, ongoing creation. I hope you had an amazing time with me here at Boring Science. I will see you tomorrow as always. Until then, stay curious, keep wondering. This is Boring Science signing off. Cheers.